All right, we're continuing with the curve sketching example problems. This is example problem number 10. In this video, we're going to sketch the function y is equal to e to the arctangent of x power. All right, step one, the domain. What is the domain of arctangent of x? It's all real numbers. You can input any number you want into arctangent of x. All right, what about e to the x? What's the domain of e to the x? That's also all real numbers. And so with that, there's no x that you can't input here. All right, so the domain is all real numbers. Now, the range potentially isn't all real numbers, and we'll analyze that later in this video. But again, the domain is all real numbers. You can input any x you want, any real number, and you're going to get an output. All right, what about the intercepts? Let's set x equal to 0 and solve for y. Okay, arctangent of 0 is 0. E to the 0 is 1. All right. Now, what about the y-intercepts or the x-intercepts? Set y equal to 0 and solve for x. Okay, so e to the arctangent of x. Store this, okay? Now, let's solve for when e is equal to 0 for x. There's no solution. Okay, so there's no x-intercepts, and there's a single y-intercept. Okay, so we're going to go from, to get the best look at this graph, we're going to go from minus 10 to 10, and then from 5 to minus 5. Okay, and so the y-intercept is at 0, 1. So here. Okay. Next, let's check for symmetry. Is this an even function? So y of minus x is equal to what? So arctangent of minus x, or e to the arctangent of minus x is what? E to the minus arctangent of x. Okay, which is not equal to the original function. So this is not an even function. What about, is this an odd function? Minus y of x is equal to minus e to the inverse to the arctangent of x. This is not equal to this. So it's not an odd function. What about periodic? Is there some number p such that y of x plus p is equal to y of x? Well, okay, arctangent is not periodic. Sine, cosine, and tangent are periodic, but it's different for the inverses of the inverse trigonometric functions. Okay, so there is no if arctangent isn't periodic, then e to the arctangent of x isn't going to be periodic. So there's no symmetry here. Next, let's analyze the endpoint behavior. So to do this, we take the limit as x approaches the endpoints of the domain of the function. So what is the limit as x approaches negative infinity of e to the arctangent of x? Okay. So we take the limit as x approaches negative infinity of the function, e to the minus pi over 2. Okay, what is the limit as x approaches positive infinity of e to the arctangent x? Okay. E to the pi over 2. All right, so what does this tell us? These are horizontal asymptotes, right? X is approaching positive or negative infinity, and as x approaches positive or negative infinity, the function is approaching a constant value. That's horizontal asymptotes. So what is e to the minus pi over 2? That's 0.20. What is e to the pi over 2? 4.8. So 0.21 and 4.8. Okay, 0.21. So this is 0.5, 0.25. So right in this region here. Okay, and now 4.8. So 1, 2, 3, 4, 4.5, 4.75. So right at the top here. There's the two horizontal asymptotes. Okay, next, let's get any critical points. Okay, so first derivative. Okay, so d dx. Okay, so there's nowhere where this doesn't exist, but what about where this is equal to 0? There's nowhere where this doesn't equal 0 either, so none. Okay, what about the second derivative? Okay, so okay, there's nowhere where this doesn't exist, but what about where this equals 0? X is equal to 1/2. So at 1/2, and then the function evaluated at x is equal to 1/2 is 1.59. There is the second derivative equals 0. So 1/2 here, and then 1.59. 1.5 about right there. The second derivative equals 0. Okay, now intervals, increasing and decreasing intervals. So there's no critical points with respect to the first derivative. So there's going to be no change in the first derivative, the sign of the first derivative. It's going to have one sign for the entire domain. What's that sign going to be? Okay, well, what we can do is plug in x is equal to whatever. Okay, so it's going to be increasing over the entire domain. It's going to be increasing. Okay, the second derivative is going to potentially change from positive to negative or negative to positive at one point. At x is equal to 1/2. And then it's going to be the concave up or concave down for every single point to the left, and then concave up or concave down for every single point to the right. Okay, so x. Okay, so we take this with x is equal to 0. So concave up to the left of x equal to 1/2, and then what about to the right? We'll put 1. Concave down. Okay, so we do have an inflection point here at x equal to 1/2, and then there's no local maxes or mins. Okay, let's sketch the curve. So we're always going to be increasing, and then here's the inflection point where we switch from concave up to concave down. So okay, so that's the graph. Now, what is the range? We can see that the range goes from e to the minus pi over 2 to e to the pi over 2, not including the endpoints, right? This is always increasing, concave up, and then switches to concave down here. As x approaches negative infinity, the function approaches e to the minus pi over 2. As x approaches positive infinity, the function approaches e to the pi over 2. Inflection point here. There's no other points like local maxes or mins, so this is it. It's not periodic, not symmetric. So this is the graph.